find the notes where we stopped. So we discussed it, sp hybridization, mixing 1s and 1p from one atom. The second example has to do with sp2 hybridization. Again, it is related to the same atom, in this case, carbon. And carbon has all kind of this sp2, sp3 hybridization in its compounds. To have a concrete example, ethane, this C2H4 is an example. So let's look at this molecule, the structure of which, and then we will do the discussion. Now, here's a top view. You look at this, the molecule lie on the plan, your head is above it, okay? So if you look at it that way, you will see very nice 120-degree things coming up. So you have this, this, this. They are all (120°), and they all form strong bonds on this. You can call it XY plane. All right. So it is rather unusual. We have the carbon, and then forming bonds with 4 hydrogen at their far ends, and then this 2 carbon can form a very strong covalent bond between themselves. Okay, but if you count the number of electrons per carbon, so carbon has 2s2 p2. Okay. In addition to 1s2, that is too deep. We don't need to consider that for chemistry purposes. They remain filled close to the its own atom anyway. So if you look at it for the carbon, it has 4 possible electrons, including the 2s2. Okay, how could that form such a bonding? All right. Now, in addition to in this way, you can think that there's 1 electron from carbon here, another electron from the carbon, and another electron from the carbon, forming these 3 strong bonds on the plan. But there are 4 electrons in this 2s2 2p2. So what happened to the remaining one? Okay, so you have 1, 2, 1, 2, 3, accounted for, and there is a 4th one. So the 4th one, you need to look at it from the side view. Okay, now this is the top view. You look at it at the side view, it's something like that. There remained another p orbital not involved in this very strong framework. So this is the framework bonding on the XY plane, very strong, because strong overlap, good overlap. Okay, but there is another one, the 2pz, from each of the carbon atom, that will form a pi bond. All right, they just barely touch each other. Nonetheless, you can linearly combine them, LCAO for the PZ, and then there will be a bonding pi and an anti-bonding pi, and the bonding pi will be filled by 2 electrons, right? Because there's 1 electron in 2pz on the left atom and on the right atom. Okay, so that is the big picture. All right, so now we want to understand something. why is there this very strong framework on the XY plan? How this 120-degree comes about? So that is the question we want to answer. And the key idea is within this sp2 hybridization. So this is the single carbon picture. So we have this 2s22p2. Again, just like the beryllium situation, the 2s and the 2p actually they are at different energy because carbon is not hydrogen. Nonetheless, in a simple picture, you may think that if I pay some energy first, that's not much to promote some electron to the 2p level, and then at the end, 4 electron may be of this kind of arrangement. Now, this is not the ground state. You already promote some electron to some higher 2p state. And then focus on 1s, the 1s electron. And then how about I call this px and py, and there is 1 electron in each of these 2p atomic orbitals. So therefore, we will focus on 2s, 2px, 2py. So px, py, you can think about it, px is something like a vector because it is directional, it's on the xy plane pointing to the x, and then py similarly is on the xy plane pointing to y. So on the left, the picture, I'm drawing it on this x-axis and y-axis. So I'm taking the top wheel now. Your head is looking at the xy plane. So the S is symmetric like a ball, no direction. Px, this dumbbell shape pointing along x. And then Py is this dumbbell shape pointing into y. All right, this is atomic physics. Recall, if you want to know what is Px, it is y11 and y1 minus 1 linear combination. You add them together, you get this x directional combination. Okay, so now we are putting in 3 atomic orbitals: s, px, py. All right. Actually, in the full LCAO, we should also consider the hydrogen stuff, the next carbon behavior. But now with the SP experience, we know that we can think along the way that now I have these 3 atomic orbitals, let's change bases, do linear combination among them and see what comes out into a way that will spread out the electron charge as much as possible. That will reduce the Coulomb repulsion. Those are the terms in the Hamiltonian of the molecule, okay? So the idea becomes, let's form linear combination. So I call the linear combined thing the hybridized orbitals C1, C2, C3, all right? They are linear combination of the S, Py, Px. Each one of them is such a linear combination, thereby we should have 9 coefficients. This time, this S is going to be shared by these 3 hybridized orbitals. It will be shared equally. I don't see how nature would, the S will bias one of them because S is rotational symmetry. It has no directional sense. Why should it go more to the X or Y or Z, okay? So with this idea, since it is to be shared within 3, so the probability of having S character in each of the psi 1, psi 2, psi 3 should be 1/3. And therefore, the coefficients for the S atomic orbital is 1/√3. So that will save us from solving 9 coefficients to solving the remaining 6 coefficients. So the S can be fixed easily, okay? We fixed it as 1/√2 previously in the SP hybridization. So now we make the same argument and do it as 1/√3. So the remaining problem is to solve for these 6 coefficients. And now I exercise one freedom. What I care is the relative direction of these 3 hybridized orbitals. Therefore, I take the first one to be aligned in Y. Therefore, I set one of them to be 0. That is no loss of generality. After I get all this, the end result is something like this, okay? In my consideration, I set one to be along Y, then I get the remaining 2 like that, okay? It doesn't matter. The linear combination at the end means you mix in S and 2 P's, you will get something like that. It could be like this, it could be like that, it could be like that, it could be like that, it could be like that. It doesn't matter, okay? If you don't like that, you can do another choice, make this 0, make this non-zero. You are putting it like that. One is along X, okay? So I emphasize that this analysis up to here is not a special case. Well, it is special in the sense that one of them is aligned in Z. But nonetheless, at the end, you can rotate all this thing arbitrarily. So I do that. Therefore, I have 5 remaining coefficients to solve. B1, B2, B3, C2, C3. Okay? Now, all the atomic orbitals are normalized. And since they belong to the same carbon atom, they are orthogonal to each other. Now, listen to this very carefully. The reason is that they are atomic orbitals of the same atom. And that goes back to atomic physics. A single atom, you solve it, the energy eigenstate of the same Hamiltonian can be made orthogonal, okay? And also normalized. And I'm exercising this property. So they are orthogonal among themselves. So now I enforce this should be normalized. That's the first thing. That's easy. Immediately I know 1/3 plus b squared is 1, okay? Thereby I solve b1 to be √2/3. So 1 is down. Then I go on to solve for the remaining one. For example, B2 and C2. After doing this, I know what psi 1 is about, okay? So it is this amount of S add to that amount of Py. You immediately see that the charge is focusing onto the Y direction. Just like SP, only the proportionality constants are different, all right? So the second thing is I want to make psi 2 orthogonal to psi 1. So how to do that? Multiply side 1, side 2 together. So you will have cross terms, right? You will see this meet this. That's fine. That's 1. Okay. When you see this meets this, nice 0. Okay. Then you will hit at a term, this multiply into that. You will have a coefficient, square root 2/3 times B2. Okay, do you follow me? All right. But by orthogonal, we mean side 2 times side 1 integrate over all space is 0. Therefore, you have an equation to solve for B2. I haven't done the algebra for you, but the idea is already there. You can solve B2 easily, and therefore, we know this. Okay? The remaining C3 can be solved by side 2 being normalized. Okay? And that is a condition you can use to solve this C2. And at the end, you get this. So therefore, step by step, we solved what is C2, the second sp2 hybridization, hybridized orbital. Okay, so we have this, and then I haven't solved the side 3 for you. I think you can now do it. Given that you have this already done, you just require this is orthogonal to that, and then itself is normalized, then you can solve for the remaining coefficients. So let's look at these 2 resulting hybridized orbitals. They are sp2 hybridized orbitals. There's one remaining to be solved. But that is sufficient for us to determine the angle. So the question now is, what is the angle in real space, the geometric angle between C1 and C2? Okay, now this thing, I think it is called xi in Greek. Okay, so this is C. So this, let's look at C1. C1, I intentionally put it into the y direction. I know that because we have this sense, S, no direction, P is like a vector. So Px is pointing to x, Py is pointing to y, Pz is pointing to z, okay? So here I have a combination, no direction, and then in y, all right? So I can represent C1 as a vector along the y direction. So this is how I represent C1. For those who don't like this, now some students are very strict in doing physics, okay? Although I have been trying hard to relax to relax your way of thinking. You should write down the wave function, and then you have a distribution in space, just like what I sketched to you, and then you look for the maximum. This is polar plot. So you look for the maximum that has the longest distance, meaning that is the highest, the focus of the probability density. Okay, the end result is the same, I guarantee. But I'm a lazy guy, so I'm doing the lazy way. Okay, so now we have side 2. Let's look at what is its direction. all right? So I exercise the same thing. This has no direction. I see something that pointing to the X. So it has an X component, but it has a Y component as well. And even I can see that it has that long X component and that long in the minus direction, a Y component. All right. So now I exercise my sense. So I draw it as this C2. You see the vector? And intentionally, the X component is this long. Okay. The Y component is in the negative direction. Okay. And it is that much. All right. Now, with this knowledge, immediately you can look for some angle, right? At least you can look for this angle. So tangent this angle will be the components ratio. It is the y component over the X component. It will give me this angle. This is this angle, all right? You do that, you will find this is 30 degrees, but there is a 90 degree here. So you add them up, bravo, we have this 120 degree explained. So we now see side 1, side 2, they make a 120 degree between themselves. Okay? So as an exercise, I would like you to find out what is side 3, okay? And then you look for the angle, how these three things line up among themselves. And it is like this. And I think for those of you who have taken some chemistry courses or did chemistry in high school, you might have memorized this thing for some years. And now I hope that you have this idea. First, that's easy, no new physics. Second, it is LCAO idea, okay? Only that focusing on linear combining the atomic orbitals from the same atom, first, we can change bases and spread out the charge. Remember, we have one electron in 2s, one electron in 2px, one electron in 2py. Thereby, you can also think that you have one electron in this C1, one electron in C2, one electron in C3, waiting to form bond with other atoms, okay? So that is the sp2 hybridization. So let's move on. C2H4. We discussed this for one carbon. We can do the same for the other carbon. As I said, that is just the relative angle. The absolute rotation is another business. And now, when there are two atoms around, there is a special direction. So this is the special direction, okay? So now you can think that these two carbon align one of their sp2 with another sp2 hybridized orbitals from the second carbon, so that they will have a very strong overlap. Recall, strong overlap means this 2 by 2 matrix from the C2 from carbon 1 and another C from carbon 2 will be pushing each other very hard. Okay? One will be pushed down, one will be pushed up by a bigger extent. That is useful because there's one electron here, one electron there. They go to occupy the pushed down state. Leaving this empty doesn't matter. energy is gained. Thereby, the bond is strong. This framework on the XY plane is very rigid. Okay, so that is the physics of the chemistry. Okay, so we now understand this carbon-carbon sigma bond formed by overlapping of the hybridized orbital. Similarly, we have 4 hydrogen, each carry 1 electron waiting to be bonded. Perfect. They go with this hybridized orbital forming a sigma bond. Okay, so you can think about this as another 2x2 matrix. Since the charge are now focused, this pushing will be stronger, gain more energy. So you have this, all right? So now at the end, this framework is formed and rather strong because the overlap is big, okay? So now the remaining thing is to take the framework, turn it over, and there are still the PZ orbitals to be considered. So we have this remaining PZ, they are not involved in sp2. They are the lonely guy not involved in this play of sp2 hybridization, but it is very easy for our consideration. After the framework is done, we don't need to care about all this px, py anymore. They are done. They already form what they need to do. So when we consider this, we need not consider all the other things again. And then it is itself just a 2x2 matrix kind of thing, because we have only 2 atomic orbitals, 1 from each carbon. Okay, you set up a LCAO, it's just a 2x2 problem. The overlap is not to be strong, they just touch each other. Okay, in this extent, so this is a pi bond. All right, so just push each other slightly, you gain a bit more energy. Okay, not as much as the framework, this rigid framework. So at the end, you have another bond here. Therefore, you have this double bond in the chemistry notation. So in chemistry book, organic chem, this molecule is written like this. All right. The first line is on the XY plane, sp2, very strong. The second line is a pi bond, which is weaker. So now we explained that. Now we sidetrack to something else to understand what is the circle. I mean, what is this thing? In the benzene molecule, all right? Now, this is related to metallic bonding, metals. So it is an important concept around. The important concept is about whether electrons, the pi electrons, the one that we just discussed. So this thing, this EZ, PEZ orbitals sticking out from a very strong framework. Do these electrons want to delocalize, or they would rather localize? Now, with only 2 carbon, there's no problem as such, because this PEZ electron will live around here. There are no other carbons to migrate, to move around, okay? But in benzene, the situation is much more interesting. The benzene structure is as follows. We have a planar, very strong framework. You see all this 120 degree structure, okay? Therefore, we need not explain the planar structure anymore. Okay, so it is better seen in this picture. Each carbon is doing sp2 on the xy plane. So here you see this carbon with its sp2, the other one with its sp2, and then they arrange each other so that they will have very good overlap. Okay, if you look locally here, it's like very much like the C2H4 structure. Only that after this hydrogen, this one is bound to the next carbon through, again, very strong overlap. Okay, so the framework is on the XY plane. We will not explain it again. It's sp2, done. All right, so this is this framework. Now, the question I want to discuss here is the following. Each carbon still has a 2pz. So this is the 2pz sticking in and out of the XY plane. So they live like this. Each has this, and also each has one electron in it. So altogether, we will have 6 2pz, each from every carbon, and then 6 electrons all together. All right. Now, there is a question. If you follow C2H4, this will form a double bond, okay, between 2 carbon. So the question is, for this pz, will these 2 form a double bond? So this one, okay, and then the other 2 form a double bond, this one, and the other 2 form another double bond, this one, okay? Will it do something like that? It's possible, right? But if it do something like that, it may as well do something like this, right? Because I could start with this 2 forming a double bond, then the other 2 form a double bond, and the other 2 form a double bond. Okay? That will be this structure. Okay? Then the question is this or that, or even something else with a circle? Okay? The answer is that it is this something else. And then we want to understand what is this something else. That's the question. Understand the question? Do you understand the question? Because the answer is very simple. Okay? Now, the next thing I really want you to do to relax your mind, okay? Don't behave like a typical CUHK physics major. Every sign must be equal, very rigorous formula stuff. We just exercise LCAO by physical sense. But it is a very powerful technique, okay? So let's do that. I will do LCAO of the 6 pz orbitals. That is to say, I'm going to form the state of these 6p orbitals in the following general way. I'm doing it as linear combination of 1, 2, 3, 4, 5, 6. By that, I already labeled the number. 1, 2, 3, 4, 5, 6. The way you label it doesn't matter. You can label it in rather strange way. You can call this 1 and then 3 and then and then 5, and then other thing. It doesn't matter, okay? The physical sense is more important, okay? So now I would like to do this. Well, that is rigorous. I have 16 only, so I need to combine them to see what happened. What will be the lowest energy combination in order to accommodate 6 electrons? Now, exercise what you learned from the first week up to now, okay? We are on the 12th week. Now, if you do a wave function like this in a trial wave function idea, you are given a Hamiltonian, then immediately you will have a 6 by 6 matrix problem, and then you can set up a determinant 6 by 6. The elements is Hij minus ESij, so there are 36 of them, and then the determinant equal to 0, that you can solve for this energy E, eigenenergy E. Since it is 6 by 6, it will be a, I don't know what's the name, sextic equation. I mean, the highest order will be e to the 6th power, and then you will get 6 eigenvalues. Okay, do you follow me up to here? I mean, gradually in the term, we should do physics in a higher and higher level thinking. By that, I mean, without writing more and more equations. Do you understand? Do you understand this line, right? Formally, right? Okay. Now, I started to think deeper. I want to construct. Because I need to do this, I want to think about what this thing should be. Okay? So let's start with Sij. I know that Sij means the following. It means this pi on the ith side and this Pz thing on the j side, and then integrate over everywhere. Okay, you understand that? This is Sij. Now that is very dirty but very beautiful. I don't even want to write down the wave function. Do you understand? Get me? Okay. Now, I know one thing for certain. Sii is 1. Because that has to do with the Pz, both of them on the same atom. So normalization, that's 1. Okay. Now, if you look at this structure formally, S12 may not be 0 because at least they are close to each other, okay? But if you look at S13, wow, they are quite far away, do you see? So that is very comfortable. You can set it to 0, okay? But for our purpose, you will see that we can simply set Sij approximately to 0 when I not equals j. That will make life very easy and don't make much error. All right, so this is an approximation I will be happy to make. That is to say, the E will only remain on the diagonal places. Okay, Sii is not 0, is 1, so I will have H11 minus E, H22 minus E, H33 minus E, and so on. Okay, do you follow me? Okay, so that is what I will do for Sij. And now, how about Hij? Okay, I know many of you will say, write down the Hamiltonian. All right, I will say, avoid writing down the Hamiltonian. How about that? I take it as a parameter. Okay, so that is what I will do. I will explain the idea. Okay, now I know what HII, the diagonal thing, should be. HII, even I write down the big full Hamiltonian with 6 atoms, it is related, from previous experience, it will be related to the atomic 2p energy. So the diagonal one, I will take it as the 2p energy because that is more like an atomic physics problem. The PZ sitting on 1 will see that part of the Hamiltonian from the 1 atom most. And then the other ones are just tiny terms. So the most important thing will be the on-site, so-called, this is called the on-site energy, meaning on the same site as the the PC electron 1, seeing atom 1. Okay, so that will not cause us any problem. Now the trick is about Hij. It will be an integral like this. Okay, now formally it is something like that. I know several things. It is an energy. Okay, because H is an energy, it is an energy. And then I start exercise the physical sense as follows. The most important terms will be HII. But that is already taken care of. It is the 2p energy of an atom. Then the second most important thing will be when I and J are nearest neighbors. What do I mean by that? If I is 1, then the most important term will be H12 and H16. Okay, do you understand? Do you understand the sense? Because at least spatially, 1 and 2 are nearest neighbor. They are nearest to each other. When you have such an integral, you need 3 of them are simultaneously not 0 in order to have any contribution. Okay? You have the PZ, you have the Hamiltonian. Okay? You need all of them being non-zero in the same region so that the integration should have a non-zero contribution. Okay, do you understand? Do you understand the point? Okay, so now what I'm saying is the following. Among Hij, let's keep H12, H16. And if you start from 2, let's keep 1, 2, and 2, 3. If you start with 3, let's keep 2, 3, and 3, 4, and so on. Get me? All right. From now on, I will use a parameter, just an energy symbol. I don't know what it is, but I don't need to know, at least qualitatively. I will call this Hij non-zero ones V, just V, okay? And I will call H11, the 2p energy, just epsilon. So I'm using epsilon and V as just 2 symbols for my 6 by 6 matrix or determinant, okay? Now, if you look at chemistry books, or actually the first one who did it is a physicist called Huckel. I think there's 2 dots there, okay? What I'm telling you is something called the Huckel theory. It's a physics topic. I know some of you hate chemistry, okay? But I want to tell you that you shouldn't hate chemistry, because physics is, explain matter, and chemistry also try to explain matter, but in different approach. So we cover a large part of chemistry. Now we are trying to explain why can we ignore S12 but not H12? Okay, now if we set H12 to 0, then all the 6 atoms will not be coupled. They will not mix. They will not push each other. Do you see? Get me? H12 is like the delta in the 2 by 2. Get me? We want to keep some pushing so that they mixed and form new 6 MO for us. Then we fill in 6 electrons and see what happened. Do you get me, Howard? All right, okay. So now life become very simple. I use epsilon for the on-site, diagonal 1, 1, 2, 2, 2, 3 elements. And then I use V, just one symbol, for the nearest neighbor Hij. If you look at other books, usually the physical chemists will use alpha for this and beta for V, all right? Let me tell you that after more rigorous calculation, usually this V or beta turns out to be negative. But that is just a detail. So for the moment, let's do that. So if you look at the benzene structure, okay, and remind you we are doing this. Okay. We can immediately jump to this line. Okay, I hope some of you, at least some of you, when you see this, after exercise your mind, the next time or the next time, from here you can immediately think, oh, it is this kind of problem. Okay, that will be very nice. So what we have been doing is that H11 is 2pz carbon 2pz energy. And we have 6 identical 2pz. So we have epsilon, 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 epsilon. Okay. And now how about H12? Now 1 has nearest neighbor 2. So H12 is V. And then 6 is also its nearest neighbor. So I put a V here. This is H16. How about H13? Wow, they are very far away. The integral should be 0. 0, 0. Okay, do you understand the first row? Okay. If you understand the first row, then exercise your quantum mechanics. You copy it through here because, they are relative, okay? Well, assume everything is real. You don't even need the star. So I copy it through. Then similarly, for the second atom, the nearest neighbor is 1, 3. Other are so far, too far away, all right? Similarly, for the other atoms, you see, each will have 2 non-zero off-diagonal elements because each will have 2 nearest neighbor. Okay? Thereby, this is the problem to solve for the 6 linear combined their molecular orbitals, the energy, E. There will be 6 results. Okay, so do that. Now, it's not obvious, but let me tell you that this can be done analytically. I mean, this equation can be solved analytically. Not too difficult. Okay, let me tell you. I think I won't tell you. Something is like alpha plus 2 beta. Okay, and then alpha minus 2 beta and so on. Okay, but don't worry. I just sketch. I leave it as an exercise intentionally. Okay, but I would like to show you the 6 energy. They are lined up as follows. 1, 2, 3. These 2 are degenerate. They are alpha plus beta. And then alpha minus beta. And then alpha minus 2 beta. Beta is minus. I mean epsilon minus 2v. Sorry. Okay. So these are the 6 MOs. The next stage, just like any problem, we call that we have 6 electrons. Each has 1 electron. So altogether we have 6 electrons. Thereby we use Pauli exclusion principle to fill them in. That is how the 6 electrons living on top or below the benzene ring will behave. So the lowest energy ground state must be 2 here, 2 here, 2 here, there. Okay? The upper 3 are empty. Okay. Just like Howard asked, what if we even ignore Hij? They will be uncoupled. Therefore, the 6 ones will all be at the atomic energy epsilon. Okay? So with this case, maybe you can do this. Each one carry its own. Okay? So now you can compare the energy. Immediately you see, all these are lower than the original atomic energy. Okay? So thereby, energy has been gained by doing this linear combination. The energy is lowered. That's the key point. Okay? So, and it is this picture of filling in the electron that give us this benzene circle. Okay? This is 80% of the story. The full story has to go back to solve for the coefficients. I mean, to solve for this C1 to C6, for each of these states, sorry. Okay, for example, what is this state? I tell you the answer. C1 equals C2 equals C3 equals C5 equals C4 equals C5 equals C6. That is the lowest, this one, linear combination. Okay, immediately see, for this particular MO, for the lowest 2 electron, they really spread out because it is a linear combination with the same coefficient among the 6. So they will spend equal weighting probability among the 6 carbon atoms. And that is why we have this circle. All right. So it is because of this analysis, we have this understanding. Earlier, we asked the following question. Will it be double bond, double bond, double bond like this? It's possible, okay? So we can propose a structure like this and see what will be the result following our LCAO analysis. So now we exercise our sense. If it is this structure, it is saying that one will only coupled, combined, linear combined with 2. So this structure means we have a V in this H12 and H21, but 1 will not couple with 6. So I don't have the V here. This will become 0. Similarly, 3 will do bonding with 4. So I have this famous 2x2 block to describe this pushing the 2p push up and push down business. And 5, 6 also do this. So suddenly my 6x6 factorized into 3 identical 2x2 blocks. And this is problem 1, question 1, right? So the answer is epsilon plus V, epsilon minus V. Okay? And you have 3 of them. So you have repeat 3 times, you have this for the 3 blocks. Each has a 1 electron, so you have 6 electrons, fill in, fill in, fill in, okay? Now compare with the uncoupled situation, this also gains some energy. Of course, it is lower the energy by pushing, okay? However, this is a big however. This has higher energy than that because I have an exceptionally lower one here, okay? This one is obtained by delocalizing the electrons, okay? So thereby, this is the idea behind delocalizing the electron can lower the energy, all right? So after this analysis, we have this having a lower energy than these 2 possibilities, okay? And there is a definition called delocalization energy. This is defined as how much energy is gained by delocalizing the energy, okay? But rather unusually, you need to do a wrong calculation first and a right calculation in order to get this difference. So it is defined as the difference between this one, higher energy, and this one, lower energy, okay? Obviously, the difference is 2 times this difference, right? Okay, because this is the same as that. Only one of these two electrons now has a little bit lower energy, okay? And that is a triumph of quantum mechanics in the early days. This theory was done by Huckel, 1931, to explain this kind of, don't know whether it is double bond or delocalizing. And the more important application is actually to understand metals. In metals, sodium, we have this, sodium is 3s1, okay? So everything is filled to 3s1, a single electron. So sodium is a metal. It forms a BCC, a body center cubic structure. And then the 3s1 electrons can wander freely inside the solid. The electron does not belong to any of the sodium atoms, okay? So you have a so-called sea of electron, and it is because of such a bonding behavior, the electrons are rather free to wander around. When you apply a field, you have conduction, and therefore metals are good conductor, okay? But that is solid state physics, but the beginning of the understanding lies in this very nice, I think very physical, transparent Huckel theory, all right? So one last page before we take a short break is that some of you may be doing final year project, etc., in some solar cell lab, doing material type of thing. Just to introduce 2 names. Very often, you will encounter two words called homo-lumo. Okay, now there's nothing. What it means is the lowest unoccupied molecular orbital. Now, obviously, these are the lowest unoccupied ones. And the HOMO is the highest occupied one. So these are the highest occupied one in the molecule. Okay. And very often, people care about this difference. It is called the LUMO-HOMO gap. Okay. So why? Because if this material is going to be used to absorb light, that will be the minimum energy of photon. I mean, the photon must at least of this energy for the electron to absorb a photon to go up to this empty state, okay? And that matter in many light emitting or absorbing devices like solar cell devices. That this difference in a bigger and bigger and bigger, now we only have 6 carbon. So in a bigger and bigger and a bigger molecules, or even extended to a solid, that become something called the energy gap in a semiconductor. Again, semiconducting material is very useful for light emitting device and also solar cell devices. That LUMO-HOMO gap becomes the energy gap between the conduction and the valence band in semiconductor. All right. Now, there are other very interesting systems this Huckel theory can be applied. For example, this chain of carbon and hydrogen. Now, I haven't written down the hydrogen. Whenever you see bonds are not saturated, give it a hydrogen. Okay, that's the rule. So again, you may think, how about this or that or something else? Will this double bond wander around? Okay, and this chain can be longer. Okay, so you will have something called polyacetylene, that you will have double bond, single bond, double bond, single bond, double bond, single bond for whatever length. And then the question again arises, is this or the pi electron can wander around the chain? Okay, so this is a fascinating topic actually. So this ends this section. The next one will be SP3. So for the moment, let's take a break, 5 minutes, and then we will finish up the SP3 discussion.